In this video, I want to solve this problem, but before going to the discussion of this problem, I'd like to talk a little bit about a different one, which is an old problem to prove that square root of 2 is an irrational number. It's well known that this is an irrational number. If you put the square root of 2 into calculator, you'll get something 1.14, then and so on. The decimal numbers will go on without any repetition. It's an irrational number. But the question is to prove that it's an irrational in fact. So the knowing that it's irrational is different, and then proving that it's irrational could be two different things. So we want to have rigorous proof that this is an irrational number. And we can prove this. The trick here is to going from the contradiction, from opposite. So you can assume that square root of 2 is a rational number. So what does it mean? So when you have a rational number, it means that there exist two integers, p and q, definitely positive, because square root of 2 is positive, such that p over q is equal to square root of 2. So here p and q are positive integers. So in order to build the contradiction, because we are assuming that it's an irrational number, p over q, and in order to build this contradiction, we need one more assumption, a holding point. So the fractions like this, rational numbers like this, they can be simplified. So even if you look at this fraction 3 over 6, it's also equal to 2 over 4, and it's also equal to 1 over 2, so they can be simplified. And every fraction has its simplest form. The simplest form of half is 1 over 2. You cannot simplify further. Imagine that this p over q is in its simplest form, which means there are p and q, they don't have common factors. So p and q, they are relatively prime numbers. They don't have common factors. And then try to do some operations on this equation. So let me multiply both sides by q, and then see that p is equal to q square root of 2. If you take the squares to get rid of this square root, we have p square is q square multiplied by 2, 2q square. Now, looking at this, we can say that we can do some conclusions. So first conclusion is that p is an even number. It's divisible by 2. P is even, because p square is 2 times q square. So if p is even number, since p and q, they don't have common factors, they are relatively prime. If q is also prime, then it would have some kind of factor of 2. So the common factor of greatest common factor of two even numbers is at least 2. So q has to be from this statement here, q has to be an odd number, right? Otherwise we will have contradiction. So now we can represent p and q as, let's say p is 2p1, q is 2q1 plus 1. Say this is even odd number. This is an even number representation of for even number for some p. Now if I replace back to the equation, I will have 4p1 square, so this one, and then here I have 2 times 2q square. So I can cancel out 2's here, divide both sides by 2, and if I divide both sides by 2, I will have the following expression: 2p1 square is equal to 2q square. So on the left of this equation, I have an even number. On the right, I have odd number. Odd numbers are not equal to even numbers. So this is the contradiction, because we had the assumption that p and q are relatively prime. So this is the simplest form of p and q, the fraction. So simplest form means we are choosing the smallest p and q, and you can't go further. And in this case, we are facing the following contradiction. We need one odd number equal even number, because it's multiplied by 2, is equal to odd number. This is square of odd number. So there are no such numbers. So which means it brings back to our original statement here. There are no such p and q. P over q is equal to square root of 2. So square root of 2 is an irrational number. Going back to our initial problem, x squared plus y squared is 3 times z squared plus y squared. So in order to prove, so the answer is already there. So no quadruples of positive integers satisfy the following equation. In order to prove this, so we have this 3, a prime number. So we can look, instead of looking divisibility, whether it's odd or even number, you can look the divisibility by 3. So looking whether a number is odd or even means you are looking for divisibility by 2. Divisibility by 3. So we will look at this equation in terms of divisibility by 2. By 3. So imagine, so since these are positive numbers, so the assumption that two numbers in the previous problem, p and q, are relatively prime will be similar. So this is some kind of, we are choosing the extreme case of the solution. So imagine that there are several numbers that satisfy this equation. So we will choose the least, the smallest of those numbers. So among those, let's say x is smallest. X is smallest. So there can be different numbers that satisfy this system of equations, but let's say among those, we will choose the one that has the smallest x. So now let's start looking. So the right side of the equation is divisible by 3, which means this is also divisible by 3, is a factor of 3. So when this sum of squares is a factor of 3, so if you look at the number mod 3, a number can give 0, 1, 2, 0, 1, 2, these remainders when divided by 3. So if you take the square of a number, the remainders will be 0, 1, or 4 squares. And this 4 is the remainder when 4 is divided by 3 is 1. So basically x squared will have only two options, 0 or 1 mod 3. So the square of a number can have a remainder 0 or 1, and their sum has to be divisible by 3. It means we have only 4 options actually. So the numbers have, like, both of them are divisible by 3, one of them is divisible by 3, and both of them are divisible by 3. So in these 3 cases, the sum will have non-zero remainder when divided by 3. So we have only first case. So basically it means that x is divisible by 3 and y is divisible by 3 as well. So if you divide this, we will have x. So let's say x is 3 times x1, y is 3 times y1, and replace it to the original equation. So I will have the squares of those numbers. So 9x1 square plus 9y1 square is 3 z square y square. Now if I divide both sides by 3, I will have 3x1 square plus 3y1 square is z square y square. If I take out the 3, so we have the equation is symmetric. So after dividing by 3, we have something similar to our original equation. So you can do this idea one more time. You can see that z and u is also divisible by 3. And then replace it by 3z1 and 3u1. And then you'll get that equation. You'll come back to equation that x1 square y1 square is equal to 3 z1 square plus u1 square. So the assumption is now here the contradiction. If we imagine that x, y, z, u is the solution of the equation, system of equations where x is the smallest, and then it turns out that x1, so like not x1, so let's say x over 3, y over 3, so y1, z1, u1, they are all obtained by dividing these numbers by 3, and z over 3, u over 3, these are also the solution of the equation. So which means we were assuming the smallest one, but we have found another solution that also works for the system of for this equation, where the first element is smaller than this one. So we chose the smallest element, the smallest number, and then we are finding that there is a number that's even smaller. So by assumption, there should not be any smaller numbers. So that brings the contradiction. So this is also the idea of proving this is also called infinite descent for to prove this kind of equations where you have one equation for positive integers and then you find one solution which is you assume that it to be the smallest according to some kind of metrics, one of them or some of them, and then you find an even smaller one. Since the idea is, since these are positive integers, you cannot go down infinitely, because the positive integers are bounded by 1 or by 0, and then if you keep dividing by 2, at some point you will start getting negative numbers if you start going downwards, or you start getting non-integer numbers. So since we are looking for integer solutions, that brings the contradiction.